see what happened that, like we have serious air pollution problem, and the people ask, okay, well, what can we do? And some suggestions come, and some very funny suggestions come actually. So it was something like in New Delhi, like the people write to the authorities that certain area is very highly polluted and certain area is clean, and they said, well, all right, this small area called Anand Parvat, okay, and one side of the Anand Parvat, you see, there was a highly polluting industries were there, and then there was the other side which was clean. So they said, in order to clean that area which was one side of the Anand Parvat, well, that was a little hill, and they said, what if we put the huge fence, okay, and if what we can do the entire ventilation and cleaning of the air, and the clean air can push the dirty air, and then the whole place can be clean. And this is general people, they can come up with some ideas. And in fact, the fundamental thing is, don't drop any idea just on the face of it. No, this is the basic philosophy of the life. Do the calculation, do the analysis, think about it, and comprehensively analyze that, and well reject it. Even if something look on the face of it, how this can happen, like, even if just it's a matter of trying it and then rejecting it, rather than just rejecting on the face of it. So of course, I'll give you some example, like that if this is done, okay, if that can be done. Because the idea started because in the water treatment side, on the wastewater treatment side, I don't know if you know about a concept called CETPs, Common Effluent Treatment Plants, okay, where the cluster of industries, like they decide, well, let's collect all the waste, okay, either pumping the waste or through the gravity, bring it at a central place and then treat it, okay. Those are called CETPs, okay. The concept was something very similar, that, well, can this, some kind of CETP, can it work out? The one suggestion was also like, if the huge tall stack, like before the, like we can, there were two power plants very close by in Delhi. Can we have the ducts coming with a lot of dust? Can they be joined and put through the one system? And of course, the distance between two power plants was about 4 kilometers or so. Of course, you all know that in water, something can be done. We can make use of the gravity, but in air we cannot make use of the gravity, and we always have to pump. And pumping is always a very, very, of course, leave aside the ducting part and the pipes that you put, the cost of pumping is really huge. Okay, so we'll get into something else. We'll kind of begin with, we have some slides here. So what I would do is, we will slightly revise few things that we did last time, and then get into something more. If you recall, we had tried to explain you what is a criteria and what is a standard. Okay, criteria is the knowledge. Okay, very important. Based on that knowledge, standards are fixed, and a standard should have certain things attached with those. Otherwise, standard is not complete, because say legal terms. Okay, if you don't want to put a legal sense to a number, then you put the guidelines and goals, okay, which is desirable concentration. Point, that is what we did last time. And if you recall, I also gave you, and I will be sending you these slides, please remind me if I don't, that how the Indian standards they look like. Okay, here you say, and you will see what all we discussed, averaging time, very fundamental thing. Okay, then you also have the places where the standard should be met, and then what is how many measurements would constitute an annual measurement. You would also be surprised that we may call this, like for example, 24 hours, but sometimes the local conditions are so, particularly in India, the power supply, okay, is so poor that you will never get uninterrupted power supply for 24 hours, especially in city like Kanpur for that matter. So it was kind of revised, again not documented, but if we get a measurement of 16 hours, even that is okay, and that could be considered as a 24-hour measurement. Okay, so what you see here is everything, how much time it can exceed and things like that. So that we had done last time. This picture I'm sure is not very clear to you, but I'll be sending it out to you through the this thing. What has been done here is I put it all the standards which are generally mostly in Asian countries and European Union and probably US EPA, and then this slide really compares these standards proposed by various countries. Here what you see is a 1, 2, 3, 4, 5, 6, 7, 8, 9. For example, let's say number 10, and 10 is let's say Bangladesh for that matter. So what you can see here is where are you here? The 10, and this, the various standard for carbon monoxide, and various countries had different averaging time you see here. And the red and blue, red and green are the things which are very, very should we say stringent standard, and red is a relaxed standard. So it is just, I'm showing you the picture to show that, well, the standards can vary from country to country, and depending on many local conditions, standards are fixed. So this just to give you a little feel. I don't know where the India would be. Let me show you. Okay, I think 16, 16 is it? Okay, so you go here 16. Oh, very poor little 16. You see here we are, most of the time we are green here. So it means somehow we have fixed the standard which are far more stringent, okay, than many other countries. So, well, I mean, you have to be careful in fixing the standard. We don't want to fix standard which kind of we will never achieve. But the revisions are going on and more thoughts are going into this one. But it's a nice picture to compare as to how other countries are doing. I also wish to define, because you see all the standards that you have seen, okay, and the methodology that is prescribed along with the standard also specify accuracy and precision. Okay, that is the standard definition of the accuracy and precision, as you see here. As you read this definition, okay, the best way to explain the precision and definition is through some picture. Okay, and suppose you know the game of board, and you throw the darts onto it, you know, like, okay, suppose the person is hitting the arrows or the dart, and he's able to hit here, here, here. Okay, what would you call this as the, is it accurate, precision, neither, or accurate but not precision, or whatever the possible combination? What would you call it? Precise. Fine. Okay, so let me say precise. What about if suppose the situation is like this? What would you call it? Accurate and precise. Would that you like to call that one? I think it is accurate but not quite precise. You see the variability. One time it is hitting here, one time here, one time here, one time here, one time here. Okay, so we can say it's a accurate because it's very, very close to this one, accurate but not precise. And if I have the picture which is more like neither accurate nor precise, and I might have another picture. So this we want to say not precise, P for precise, and not accurate. And then we might have another picture here. And everything is right here. This is precise and accurate. Okay. Sometimes we know the accurate value, sometimes we don't know the accurate thing. Because if I ask you to do the measurement, let's say for sulfur dioxide, well, you can never know if it is very, very accurate. But sometimes you see the methods are described, because some of the methods those are developed, they are developed for the known concentration, okay, and then what they will do, they'll try to simulate the atmospheric conditions and then do the measurement and say, and they know exactly what amount of sulfur dioxide that has been put, and they'll say this method is so precise and so accurate. But still, I mean, you can hope the things will be accurate here, but yes, the methods are generally defined in terms of its precision, okay, because accuracy, sometimes you are not quite sure if the things are quite accurate. This is something very similar to what I said. So this is just a repetition of this, but you'll have those in slides so that you can kind of, refer it again and again if needed. Okay. Oh, well, more better picture than what I draw here. See here, a little bigger picture. So it is kind of accurate because you are very, very close to the target, but it is not precise. But here, for example, everything is right in the circle. So what you see here is precise as well as accurate. So you should have this concept. Okay, there's another new thing which is coming up in the air pollution, and we are still kind of talking introduction to air pollution, still haven't got into the physics and chemistry of air pollution. So this is another thing which is coming up, is hazardous air pollutants. Everyone wants to talk about HAPs, because the reason is that the other pollutants that we were talking earlier and try to give the standards. What were the names that we gave to those pollutants? Criteria pollutants. Okay, you remember 6 criteria pollutants which we wrote down? Okay, let's revise those because everyone would like to refer those 6 criteria pollutants: particulate matter, sulfur dioxide, NOx, ozone, lead, and carbon monoxide. And apart from PM, which stands for particulate matter, there are the standards. Now the other part is also considered as the criteria pollutant, which are the subset of the total particulate. Is, if you recall, I try to define as PM10 and PM2.5. Perhaps we'll explain more about PM10 and about PM2.5 in the next class as well. Okay, so about the particulate matter, there is a bifurcation, and these will be the particles of the size less than or equal to 10 micron, and that will be less than or equal to 2.5 micron. Good. So we are talking about the HAPs, and what you see about the HAPs are the sources, hazardous pollutants. US EPA, okay, have identified 188 chemicals as the hazardous air pollutants, okay, and most of the countries have accepted those pollutants as the HAPs. For example, what are the HAPs may include? The benzene, formaldehyde, cadmium, and many more things. Okay, if we go to US EPA site, okay, www.epa.gov, and you can access all 133 HAPs, and of course we are not writing on those. The problem with the HAPs are they are commonly found in the atmosphere, some of them, and some of them are found in a particular environment depending on what kind of industries is in the surrounding area. Okay, for example, if you go to the refinery, for example, okay, we in India have the second largest refinery, and where is that? No, the Reliance refinery in Jamnagar, somebody said. A very large refinery, very, very large refinery. If you go in that area, you may find some of the pollutants which otherwise you don't find even in urban environment. So that HAPs become quickly a matter of concern in that particular area. So we should at least know what these HAPs are, okay, and HAPs are more toxic than the criteria pollutants that discussed. They may reasonably be expected to result in serious irreversible diseases including cancer. Okay, so we all the time trying to talk more about the public health, and even the heavy metals, some of the heavy metals comes into that one. Okay, some of the VOCs, okay, many of the VOCs will come into that category, many of the pesticides, okay, that come into that category. And the problem with a little bit of these the compounds which are HAPs, if you look at the kind of dose response that we have been discussing ever since, there is a response here, and here is the dose, it does not show any kind of threshold. Okay, so you might find something like this, and then you don't find any threshold. This is a picture particularly true for HAPs. Unfortunately, you won't find all 188 HAPs, like in the environment. It again depends on the specific area. So, but what has been done that, well, it's difficult to control and talk about the certainly all of these chemicals. So what people have done, or what the scientists have done, they found out some 33 HAPs which are commonly found in the urban environment where most of the people reside. Okay, so I don't know if I have the slide here. Okay, the sources of HAPs you can see. In fact, you will be surprised that you wouldn't know, but the dry cleaning is one of the very open operation that happens. Like it's a very serious environmental problem. But we have to live with the dry cleaning thing in the urban environment. Okay, solvent cleaning, secondary lead smelters. You know what is the difference in primary and secondary lead smelters? Okay, the primary lead smelters are those integrated large smelter plants where the ore is processed to produce the lead. That is a primary lead smelter. But somehow the lead is already being used, and then want to extract or recover the lead from somewhere. For example, all the batteries will have lots of lead. Okay, in fact, the major lead goes into the batteries, and these batteries, like after they have lived its life, okay, they are taken back and the lead is recovered from there, and this is called the secondary processing of the lead. Okay, so that happens a lot, and a lot happens in Kanpur particularly because of the power situation, and the we have the many industries here which do the lead smelting here as the secondary lead smelting. You also can see that, okay, apart from the chrome plating which is going on, commercial sterilizers and things like that. So many of the sources are like the mobile sources, that somehow from the automobiles some of things may come, some of this is from the particular area it may come, and from point source means from the chimney, and point sources include the large industrial complexes, especially the refineries, chemical plants, oil refineries, steel mills, aerospace manufacturers, marine tank vessels loading and things like that, as we were discussing. So these are the major sources. They can also be transported, sourced from the mobile and station sources, man-made, and then the thing which you need to see, and we'll spending some time in this lecture, is the pollutants are the common pollutants, okay, and they can be and then they could be chemically transformed. We should also think there are hydrocarbons here, and they can be formed into the another pollutants in the atmosphere. Okay, and in this primary pollutants, how they are formed in secondary pollutants, and they are transported. So some of the hydrocarbons which are HAPs could give rise to the secondary pollutants which are never emitted from the source. We'll talk about that in a moment, but let's finish the discussions on HAP. This is a little, I'm just giving an example of some 20 odd HAPs here, okay, and this part was done a little bit, we did something that how to prioritize the HAPs, okay, we can't control every one of them. So what we did here is that you see the list of the HAPs. In fact, we put all the entire list of HAPs as you see here, but okay, and then you see here we looked at the emission quantities. Okay, it's not in India, but it is from US. Okay, but this part of the work, as you see here, was done here. So what we did is we want to find out and prioritize that which one is that we should control it, which should target. Like we can't do everything. So you see here there is the emission quantities, and hoping that the emission quantities we don't know in India, but the way the normal urban life, which is probably the similar everywhere, in a relative sense, okay, the emission quantity will be in the relative sense similar. In the sense this will be more and this will be less and that sort of thing. Okay, and then what was done was the unit risk factor is some measure of toxicity. Okay, here you see here the measure of the toxicity here. Okay, so if we multiply the quantity and the toxicity, okay, and that will be the more is the quantity, And suppose more is also toxicity, so the product will be even larger. So it means it is a serious problem. Whereas a pollutant may be very high, the quantity may be very high, okay, and the toxicity is very low. Okay, in that the impact will be low. So that is how this factor was derived. And if I am right, you can see this is already put into the decreasing order. So what you will find, the formaldehyde is kind of very toxic, both because it is toxic as well as emitted in large quantities. Okay, so this is what is a serious thing we should do. Okay, trichloroethylene. See the benzene, 1,3-butadiene. So now what we are proposing in India is that, well, at least we can't do anything much about these things, but let's take the formaldehyde as one of the pollutants that we want to control in India, because this may cause a serious problem. Both the quantities are high, risk is high. The benzene we all know, so benzene becomes an important thing, and that sort of thing. So that you can even handle the HAPs. And then the first step for the HAPs, what the world is doing is not to provide a legal value to that, but you say, okay, we are trying our best to control them. Okay, because you see, even the measurement of these things will not be so easy. Okay, you will require the sophisticated instrumentation, the sampling devices, and things like that. So, but what they are doing is, well, at the source, okay, they do the source inventory, and then they check the leakages there, and then the emission quantity, they say, well, the factory should try its best to control that. Okay, now we are into something again still basic, and you should know about this, is the forms of the pollutants. Okay, normally the physical form, as you will see, are solid, liquid, gas. Okay, here the solid, but in air pollution thing, all right, you see the liquid is missing. Do you see the liquid here? You don't see the liquid. So normally what we do is we consider, even if there's some pollutant which is in a liquid form or some kind of mist for that matter. For example, we may have the sulfuric acid mist in the atmosphere. We might have the nitric acid mist in the atmosphere, but we'll still consider it as the solid. So we don't take that as a separately. So there it goes. It includes the acid mist even as the liquid. And normally water is never considered as a pollutant. So we see them as this thing. And the gaseous pollutants, we are giving an example. Some of the pollutants, okay, which are semi-volatile, they can partly be absorbed onto the solid, and partly they can be in the vapor phase. Okay, so some compounds, okay, or some pollutants can be, especially like the PHs, okay, they can be in the partition between the solid and the gaseous phase. Okay, give a little feel. If I have a volatile compound, or everything is volatile or non-volatile, but among these pollutants, for example, I have a heavy compounds which are large molecular weight, and the same category of compound is low molecular weight. Which one is will be in the gaseous phase, or which one will be in the particulate phase, or which one could be partitioned between gas and the solid? Low molecular weight compounds will be completely in the volatile phase. The very heavy compounds will be completely in the solid phase, and the compounds which are somewhere in between, they can very well be partitioned between the solid and the gases. Okay, the compounds which are in the gaseous phase, how would you like to measure them on the which system? Will you want to measure on gas chromatography or liquid chromatography? The gas chromatography, because they can be very easily put into the vapor phase or the gaseous phase, right? And gas chromatography is based on volatilization of something. Something which cannot be volatilized, we would like to do it on HPLC, high performance liquid chromatography, or that can also be done on GCMS. But depending on the compound that we are trying to do, can also decide the instrumentation. Of course, that you probably will learn in some other course, but just notice that some of the compounds can be, and you will also feel that if the temperatures are high, the compound is likely to be, even if the molecular weight is slightly higher, it may be in the vapor phase. So in fact, same compound, okay, it may be, if you want to do the complete sampling of that, that may require collection on the solid phase as well as in the gaseous phase. Otherwise, you will be reporting only the part of the concentration, or the part of the fraction only you are capturing. So this becomes a little tricky. Okay. So we are not talking about the sampling analysis of those, but just these are the little things you should be aware of. Okay. And as you do more advanced courses in this one, you will learn more about this one. Okay. Well, if there is no question, let's also talk something very important. I told you about two things, the primary pollutants and the secondary pollutants. Okay. Let's see what the definitions are. Directly emitted from an air polluting source. Okay. They are at the source, they are in the chimney, they are in the exhaust. Okay. That pollutants are we call as the primary pollutants. An example you can see here, particulate matter, sulfur dioxide, NO and NO2 also. Okay. Once they come into the atmosphere, they can undergo the chemical reaction well within themselves, or the primary pollutants plus the atmospheric constituents. Okay. They can react, okay, and they do react very significantly, and they produce something new compound which was not even there in the atmosphere. So those pollutants are called as the secondary pollutants, and the definitions are these pollutants are formed in the atmosphere due to reaction amongst the primary pollutants or other constituents of the atmosphere. Okay. We'll talk well, so you see the interesting part is that particulate matter can be emitted, okay, they can as well be formed in the atmosphere. Okay. See here, for example, NO2, it can be emitted from the source as well as it can also be formed in the NO2. Okay. H2SO4 is largely formed in the atmosphere. Ozone is almost 100% formed in the atmosphere. There are some small sources may be there. Look at the ammonium sulfate. I mean, this could be formed in the atmosphere, and this is what little bit we'll see. But I normally tell this at the later stage, but it might be a good idea to know. Okay, suppose this is my chimney. Okay, we're just specifically talking about NO and NO2. Okay, and this is dispersing, and it is coming to the receptor. Okay, and reaching to the receptor. Okay, and by the time it travels, okay, you will still find NO and NO2. Okay, so the interesting part is, and thing which you should really know is, at the source, what do you think will be, well, of course you don't know, but take a guess. What will be more, NO or NO2? Okay, it says NO2, somebody might say NO. Well, fair enough, because you don't know about that, but you'll be surprised that at the source about 90% or more, in fact. Okay, we'll do these calculations, we'll show you, we'll go through the combustion process, and I'll show you that why NO could be 90%, or in fact 90 to 95%, and this could be about 10%. And as it travels, okay, the picture is reversed. Okay, this NO becomes nearly 10%, approximately. I mean, you should not go in absolute numbers, you know, like, because you may find something different and you say, well, you said something and we are finding something else. All right, then we might, this get is about 90%. Okay, and if you recall, I also had given you a term to explain NOx was NO plus NO2. Okay, why we are discussing this is if I am defining NOx NOx here, what I'm really predominantly, which one is I'm really referring to? I'm referring to NO. So if I measure NO here at the source, and can almost say this is NOx, okay? Because I know at the source, inside the chimney, the emissions will be largely NO, okay? That will do some calculation, do some thermodynamics to show at some stage, and at the source, if I'm calling, oh, the NOx level is so much, okay? So NOx at source, let's say, is 200 ppm, that's parts per million, and here NOx is, let's say, 1 ppm, which of course will be very, very low. But the NOx, the meaning of the NOx here at the receptor and source is entirely different, okay? Because here the NOx will be largely NO2 and here NOx will be largely NO, okay? And we'll show at some point, but it might be a good idea to have some knowledge as to, and then you see here almost insignificant NO2, which I don't even want to call as a primary pollutant because the quantity is so much, but here it has become a secondary pollutant, okay? And then primary pollutant, the primary pollutant was NO, and kind of secondary pollutant is NO2, okay? And then this is what is done. And now people are talking that, well, something should be done because this could always be confusing unless you are into it, and then people might just get confused, NOx measurement at source or NOx measurement at the receptor. So another funny story goes that lots of people learned, like especially people learned quickly, because this measurement of NO is a little more difficult, okay? And NO2 measurement is not so difficult. So people in the ambient air at the receptor, the breathing level, were measuring mostly NO2 and happily calling it NOx. Fair, reasonable assumption, okay? So then, you know, that people started talking, oh, we should also measure at the source. And they used, because they didn't realize this kind of thing which may exist. So this method was very easy to do, and they did the sampling here, and then they're only measuring NO2 and still calling it as NOx, thinking that, well, NO2 is largely the NOx, and they found something like 30 ppm or something, or even less actually, close to about 10 ppm. And they said, look, how low are the emissions of the NOx, okay? This is really, I'm telling you, this is a true story, okay? And then, therefore, I mean, you see, there should be a difference between some people who can just do the measurement, and what is more important is understanding of the process, having the knowledge of the process, okay? And if you had the knowledge, you will quickly catch him and say, well, come on, you're talking something, and always about the data and the numbers, and I do tell all my students, is get a feel of it. You know, don't accept the numbers as such. See, look at with your knowledge and science you have, look, is the first analysis of the data is just scanning the data, and that tells a lot of things. And they quickly will say, oh, well, there looks something wrong, because at the source, NOx can be 10 ppm, it cannot be, okay? So, well, we are drifting from our side, but let's drift, doesn't matter. In fact, some standard for the NOx was fixed. As you have the standard here, you also have the standard that could be allowed, and some standard was fixed as 200 ppm, because that was borrowed from somewhere else. We all borrow the things, okay, fine, okay. But the method wasn't prescribed. So people use the method what they knew, and they always reported as NOx as 10 ppm. And they always said, oh, we are meeting the standard, we have no problems, our process is very clean. But the foolish thing they were doing was, they were only measuring NO2, because they only, I won't say no, but they only used that method which they were measuring in the ambient air to refer as the NOx. So now the recent thing which is being talked about, or they say, well, you should measure both at the source, NO, NO2, and if you don't measure NO2, fine, fair enough, at least measure the NO, and quickly this number, as people are reporting, or the industry is reporting as 10 ppm, will quickly change, okay? It's just a little story, but then we have to be very careful with the numbers and things like that. Reasonability of the number is so important, okay? and you can very easily, and then you all have the checks and balances if you have the knowledge. Okay. In the water pollution or in the water parameters, a person will come with analysis. You can easily find out if there's something wrong with the analysis or somebody is trying to cheat on the numbers. It's quite possible, because you understand all the physics and chemistry behind it and things like that. So we're talking about that. Okay, let's see. Okay, some more examples as to how how the secondary pollutants are formed. And let me also tell you that some of the secondary pollutants, or not even some of the, most of the secondary pollutants are more deadlier than their parent compounds. Okay. So when you talk about the control of the secondary pollutants or the management of the secondary pollutants, you must manage the precursor pollutant. Okay, because you have no ways and means, because you can't tackle the atmosphere, you can't tackle the transport mediums. In water probably you can tackle. Okay, you can hold on to the water and say, well, before it is discharged, we will do something to the water. But the air volume, you can't hold on to the air volume. Look, hold on, that we will make sure that the secondary pollutants are not formed. Well, you can't do that one. So the only ways you can control is the primary pollutant, and most of the time the control of the primary pollutant is dictated by the potential it has for the making secondary pollutant, because secondary pollutant might be or generally is more hazardous. In fact, I'll give you the example, NO has almost no health effects, whereas NO2 significant health effects. So when I want to handle the NO2, I would ask the industry to control NO. It will be foolish for me, oh, NO2 is a problem, then you talk or you can do, oh, industry, you should control NO2. No, I want to handle this NO2 because NO2 is a serious problem. I'll ask industry to control NO, not NO2. Okay. So these are little things, subtle things, but very, very important thing, and that's why we should understand the science and the knowledge we should acquire. Okay, very quickly. Okay, you have here the simple reactions. You may have the acidic gases, SO2, NO2, and things like that, and then alkaline particles like the calcium carbonate may be there, ammonium chloride may be there, and then what they would do is they will react, and then they can make the salt particles. It is like a huge reaction chamber, the atmosphere, and you will see here and you will see here the particulate matter being formed. Okay, we'll talk a great deal about this one, but it is just at the time we're just introducing that you clearly understand the primary and secondary pollutants, because they indeed have very serious bearing onto the control of the pollutants. Okay, and how to manage the air quality. Our always remember, our objective is to safeguard these people. Okay, so these particles could be formed, and then you can see the dust levels going up, and you say my chimney is very clean, there is nothing that I am polluting, and why I still have so much of haze in the atmosphere, and mostly the haze that comes out is from the similar kind of reactions. And we are not talking the complete picture. Complete picture in the atmosphere is very complex, and many times we understand something and many times we don't understand something. So in fact we do lots of reaction chamber studies and control studies and things like that. Okay, some more example. See here you have SO2, okay, and in that mass suppose you have some catalyst, okay, particulate catalyst. To give you a little example, suppose you have the vanadium in the atmosphere, vanadium or vanadium pentoxide, V2O5, okay. This catalyst can quickly help convert SO2 into SO3. Okay, and once you have SO3 and you have a little water and oxygen, and this catalyst in time of vanadium pentoxide, and then quickly the whole thing will convert. So first SO2 will go into SO3 and the water, and you will quickly produce the sulfuric acid. Okay, this could be a very fast reaction, provided you have the catalyst. Otherwise, there are other ways for the slow reactions also. Just giving you the example. And the source of the vanadium, you see all the diesel and heavy oils contain a lot of vanadium into it. So vanadium is emitted. And look at the ammonia emissions which are there. Ammonia is there in the atmosphere, and ammonia and H2SO4 very quickly, provided you have humidity and other conditions, quickly form the ammonium sulfate, and very fine particles of size less than 1 micron. Okay, and you see a little haze in the atmosphere, and like that sort of thing. So look at that, where we started and where we are reaching. So when we are talking about the management, the control, sometimes we need to, and you see, we understand the chemistry part of it. Then we may say, well, we might decide to, well, take a gas. I mean, suppose I want to somehow, like control the formation of the ammonium sulfate. I might do a little bit of optimization, go through the process and go through the control technology, and then might decide, well, if I take out this catalyst from the atmosphere, okay, or if I handle the source of catalyst in the atmosphere which is causing conversion of SO2 to SO3, I might not even be forming the little haze that you see in the atmosphere. So all kinds of, it opens up, like many avenues, if I can say, as to for the scientist, engineer to control and manage air pollution. So that's what is. I'm giving you some examples. Things are very complicated, not easy, but we are still at the introduction level. More of the things you may have, as you have seen, see NO, and if you have little ozone, NO will goes into NO2. In fact, this is what most of the time we are emitting NO, but we are getting the atmosphere as NO2. Okay, and then you can also see some of the hydrocarbons and the system of the gases, NO, ozone, and NO2. See here, and you have lots of free radicals in the atmosphere. They are there, and then they can form ozone. Generally, as I said, ozone, the primary source of the ozone in the troposphere is almost not there. Okay, stratosphere we are not talking about. So most of the ozone is formed as a secondary pollutant. We are not emitting it from any source. No power plant or no car will emit ozone. Okay, but they will emit NO, they will emit hydrocarbon. Solar energy is always there. Some of the hydrocarbons are there. This again we will talk in detail. But that can yield, or that can give out as the ozone as a form, this one. And ozone is a serious problem. It's a standard question. While ozone is a boon, okay, in the stratosphere, and it's a I don't know, it's a curse, if I can use the word. It's a curse in the troposphere. So see, it's a curse here, and when I go to stratosphere, I require it. Okay, so this is what a little thing which I am going through this one, but some of the things we'll talk in great detail. But you also see a picture here. So again, to show you that, well, that could be natural sources. These are the primary sources, as you see here. These are the primary sources, go into the atmosphere, do lots of reactions, and then what you form here is the secondary pollutant. You can't see on the back probably, sulfur trioxide, HNO3, H2SO4, pH is ozone here, H2O2 is formed, very significant amount. Most you form the nitrate and sulfate salts, and that gives rise to the particulate matter. So in fact, you will be surprised that in India the major problem is the dust. You see the particles. Okay, you travel to other countries, especially European countries or North America, you don't find so much of dust. Okay, and then the question is that, and then of course we have been trying to control very hard the emissions from the power plant. Still we get the dust, is because of the secondary reactions that are taking place, and here most of the reactions are largely triggered by the UV radiation, and the UV radiation and the solar radiation, and we have lots of sunshine, and as a result our reactions and our pictures will be very different. So we will have the hazy conditions more frequently than this thing. So we probably have a greater challenge than many other countries when it comes to air pollution, because these all are the function of temperature and the radiation that are coming. High temperature, very conducive for the reactions to take place, and we have lots of energy, okay, in terms of because we are the tropics and things like that, and then as a result we have more complicated things. We'll talk in great detail about this one in this course, probably in few classes from this thing. Before we go to this, okay, at least let's discuss question number 1, okay, and then I'll take this one out and discuss something else. This is a question that I want you to do it honestly, but don't submit it, okay. Okay, the area of Kanpur is just a simulated problem. Okay, the area of the Kanpur city is, let's say, 20 kilometers by 30 kilometers. Okay, the height of heavily polluted air, we can think up to 1 kilometer the pollutants are there, is 1 kilometer. One solution to Kanpur problem would be to pump out the Kanpur air once in 24 hours. Okay, and we pump out from the upstream here, because the air this side is better, and as we move towards the city, the pollution levels are high. Okay, through a pipe. Okay, suppose it is decided to pump out the Kanpur air once in 24 hours towards the city of Lucknow, which is about 80 kilometers away from Kanpur. So what I'm saying, more of hypothetical thing, we all understand, I'm providing a pipe, okay, from the Kanpur city to go all the way to the Lucknow, and this will drive it out from there. And then you have to, I'm giving you the velocity of the air pipe is 5 meters per second, find the diameter of pipe. Any 10th class student will do that, but do it again. Find the pressure drop, because all the time we are handling and we are dealing is with the energy issues as an engineer. Okay, a successful engineer is one engineer who can reduce the energy usage, and you will be the top at the company. Okay, so we are trying to look at examine the issue as to what will be the, okay, well anyway, let's see how far we can go. Okay, so you consider the frictional losses, okay, and there will be losses at the entrance of the pipe, there will be losses at the exit of the pipe, okay, and K exit and K entrance, you recall from your Bernoulli's principles, okay. So use this value, and the relative roughness, what is the relative roughness? Where you use the relative roughness? Friction, to find out the coefficient of friction. And what charts do you use for that? Moody's chart. So look through this one, take the Moody's chart, and I want you to find out the pressure drop. Okay, and pressure drop is nothing but the energy. To estimate the pressure drop, okay, between the two ends of the pipe, estimate the power requirement of the pump that you will install to pump out the air, okay, and then if I say the power requirement of the Kanpur people is 0.5 kilowatt per person, okay, what population equivalent of the power will be taken by the pump, okay, and then do all the calculation. Is the idea workable? Okay, but obviously we know that this way is not going to work. We'll need huge amount of power, but still do the calculation and things like that. And the second part we'll do it in the next class, and we'll spend some time on to talking about the units, okay, because what I have not done is I'm using very frequently ppm and micrograms per meter cube and things like that. I'll derive a simple expression, it takes about 5 minutes, but in view of the class they have, we'll stop it here, and then we'll continue further. That is tomorrow, right? Okay, great, we'll stop here.